we find molecular geometry. In doing so, we write electronic domains and we find out geometry of the molecule or ion. Likely in today's class, we take only one central atom type. We also discuss hybridization and we count number of lone pairs and sigma bonds and the pi bonds, the type of the pi bond and where the lone pair is located, and all these calculations today we are going to do. So take heading molecule, geometry, hybridization and the type of bonds and how they are formed. Okay, let's start with a simple molecule, ammonia. Let us take a simple molecule, ammonia. So nitrogen belongs to 15th group, 5 valency electrons. Each hydrogen forms one single covalent bond. Therefore, nitrogen uses 3 electrons to form 3 single covalent bonds and nitrogen has one lone pair. Therefore, nitrogen, a lone pair, 3 NH bonds. According to VSEPR theory, 4 electronic domains, it could be tetrahedron, but with one of the electronic domain is a lone pair. Consequently, it occupies one of the corner of a tetrahedron. The molecular geometry now turns to be pyramidal. So what is this geometry we call? We call it's a pyramidal. So ammonia molecule has a pyramidal geometry. Now telling hybridization. How to tell hybridization? Count number of lone pairs and number of sigma bonds. Now see here, this is 1, 2, 3 sigma bond. Therefore 3 sigma bonds plus there is a 1 lone pair. So number of sigma bonds plus number of lone pairs. This is going to be 4. Now there are 4 hybrid orbitals. And why 4 hybrid orbitals? As we discussed it so far, in most of the cases, hybrid orbitals only form sigma bonding and lone pair or unpaired electron is present in hybrid orbital. So we get 4 hybrid orbitals for which hybridization? sp3 hybridization. Therefore, nitrogen in ammonia is sp3 hybridized. Here we have 3 sigma bonds. And all these sigma bonds are formed from sp3 hybrid orbital of nitrogen overlapping with 1s orbital of hydrogen. So this is nitrogen sp3 hybrid orbital overlapping with 1s orbital of hydrogen atom. Total we have 3 such sigma bonds. Now let us take next molecule, ammonium ion. NH4 plus. Please note how to write Lewis dot structure and of course the molecular geometry from VSEPR theory. What I said, if you find positive charge particularly on central atom as N plus, then let us make number of valence electrons now 4 and there are 4 valence electrons and it can form 4 sigma bonds with hydrogen. Therefore, the geometry of the molecule becomes N, H, H, H and H. So there is a total positive charge somewhere. So according to VSEPR, there are 4 electronic domains. If 4 electronic domains, then actual structure is tetrahedron. If all electronic domains are identical, it is perfectly tetrahedron and there is no distortion. So we call it tetrahedron. So the ammonium ion has tetrahedron structure. Now count number of sigma bonds. We have 4 sigma bonds and 0 lone pairs. So number of sigma bonds plus number of lone pairs is equal to 4. Therefore, nitrogen in ammonium ion is again sp3 hybridized. Now coming to the type of bonds. Here there is no lone pair. We have all single bonds. So how many? We have 4 sigma bonds and each sigma bond is formed from sp3 hybrid orbital of nitrogen overlapping with 1s atomic orbital of hydrogen. So overlapping with 1s atomic orbital of hydrogen. Now let us take another molecule, amide ion, NH2 minus ion. Now in case of amide ion, nitrogen belongs to fifth group, N minus. Let us consider that additional negative charge on nitrogen. Therefore there are 6 valency electrons. As we know that hydrogen forms only single covalent bond. Therefore N, H and H. Nitrogen atom in this case used its 2 unpaired electrons, total 6 valency electrons being negative. Therefore we have to make 2 lone pairs. Now count number of sigma bonds 2 and number of lone pairs 2. 2 plus 2 is 4. Again, when we get 4 hybrid orbitals, generally in simple cases it is sp3 hybridization. And now we can say that there are 2 sigma NH bonds, and each sigma NH bond is formed from overlapping between sp3 hybrid orbital of nitrogen with that of 1s orbital of hydrogen atom, and 2 lone pairs are present in 2 hybrid orbitals. So the geometry of amide ion we call in general bent. What we call it? It is a bent molecule. Now let us use some more simple molecules. Take water molecule H2O. Now oxygen belongs to 16th group. So what do we make? Oxygen. There are 2 single bonds. We know that in VBT, first we always write one sigma bond, then only there is a possibility of formation of pi bonds. Each oxygen atom has 2 lone pair. The geometry remains the same. It is a bend. Now the calculation also remains the same. So the calculation remains the same. Here we have 2 sigma OH bonds. We call sp3 hybrid orbital of oxygen overlapping with 1s atomic orbital of hydrogen. So we got 2 sigma OH bonds, and as usual 2 lone pairs, and each lone pair is present in 1 sp3 hybrid orbital. Now the fifth case, consider hydronium ion H3O plus. Oxygen belongs to 16th group, 16 valency electrons when we have positive charge. Now let us assume that oxygen has now only 5 valency electrons. The geometry becomes equal to 3 hydrogen bonds, and there is 1 lone pair on the oxygen. What is the geometry called? This geometry is pyramidal. Now count the number of sigma bonds 3 and number of lone pairs 1. Total become equal to 4. Again it is going to be sp3 hybridization. This is again going to be sp3 hybridization. Now we have 3 sigma OH bonds, and each sigma OH bond is formed from overlap of sp3 hybrid orbital of oxygen atom with 1s atomic orbital of hydrogen atom. Here we are always looking at sigma bonds. We have not yet written any double bond system. Now let us start with one double bond system. Start with simple molecule sulfur dioxide or SO2. And for this molecule, sulfur belongs to 16th group. Oxygen forms 2 bonds. Therefore, each sulfur should form 4 covalent bonds in SO2 molecule, and 1 electron pair is left as a lone pair. So what we write? Lewis dot structure, and then valency shell electron pair repulsion theory. S double bond O, there is a lone pair. The geometry is bent. There are total 3 electronic domains, so geometry is bent, and we don't call it is a trigonal planar. Why? Because the electronic domain is trigonal planar but the other than electron pair, lone pair electron, other than unpaired electron, other than lone pair, the remaining electrons called bond pairs decides the geometry. So we call it simply bent structure. Now the number of sigma bonds, see that here we get one sigma bond between sulfur and oxygen, here another double bond and therefore one sigma bond, and the next bond therefore should be pi bond. So therefore the SO2 molecule has two sigma bonds and two pi bonds. Now to know type of hybridization, so count the number of sigma bonds, there are two sigma bonds, and count total number of lone pairs, there is only one lone pair, so 2 plus 1 becoming equal to 3. So generally which hybridization leads to 3 hybrid orbitals? Of course it is sp2 hybridization. The actual structure of sp2 hybridization is trigonal planar, one lone pair occupying the corner of equilateral triangle. And here we have sigma bonds as well as pi bonds. Now let us talk about sigma bonds. There are two sigma bonds. Each sigma bond is formed from sp2 hybrid orbital of sulfur overlapping with, please note that in oxygen atom in its ground state there are two 2p atomic orbitals each having one unpaired electron. Therefore it overlaps with 2p of oxygen atom, and there are two such sigma bonds. We have two pi bonds. In addition to that we have two pi bonds. Now where do we get these two pi bonds? Now pi bonds are formed by hybrid orbitals. Pi bonds are formed by unhybridized orbitals. So in among two sigma bonds we got two sigma bonds from two sp2 hybrid orbitals, and one sp2 hybrid orbital contain lone pair. Here one hybrid orbital, sp2 hybrid orbital contains lone pair. Now to form a pi bond, sulfur either use one p orbital or one d orbital. So here we have two types of pi bonds. Pi bond 1 is formed from 3p orbital of sulfur, overlapping with 2p orbital of oxygen, which is generally called p pi bond. This is generally called p pi bond. And second pi bond would have been formed from, as all 3p orbitals been used up by sulfur, now the next pi bond only comes from the next higher energy orbitals. Here sulfur 3d of sulfur overlaps with 2p atomic orbital of oxygen. Therefore another bond is becoming d pi. We call it d pi p pi bond. We call it d pi p pi bond. Therefore in sulfur dioxide we have one p pi bond and one d pi p pi bond. The importance of this bonding we discussed in the concept of resonance, and why we are selecting one oxygen for p pi and why other oxygen we are selecting for d pi p pi. I will explain that in detail in the concept of resonance. Now let us take example of sulfur trioxide. Here I am directly writing its geometry by applying VSEPR theory. S, double bond O, double bond O, double bond O. What is the geometry called? Trigonal, planar, trigonal, planar. So maximum all four atoms are on the plane. Now I am counting number of sigma bonds. Of course there are three sigma bonds. 1, here 2, and here 3. There are 3 sigma bonds, and there is no lone pair on sulfur because sulfur has been used all of its valency electrons. You can count it if you want. 1, 2, 3, 4, 5, 6. Sulfur belongs to 16th group. It has used all his valency electrons, 6 valency electrons. Therefore there is no lone pair. Now if you write number of lone pairs and sigma bonds, there are 3 sigma bonds and there is no lone pair, that is 0. 3 plus 0 becomes equal to 3. Now which hybridization leads 3 hybrid orbitals? And it is very common, sp2 hybridization. Here again we have 3 sigma bonds, and each sigma bond is originated from sp2 hybridized sulfur atom, sp2 hybrid orbital of sulfur atom overlaps with 2p atomic orbital of oxygen, and we have such 3 bonds. In case of pi bonds, we have 3 pi bonds, and here 3 pi bonds all are not identical. And see here, one pi bond, first pi bond is formed from unhybridized p orbital, 3p orbital of sulfur overlaps with 2p unhybridized orbital of oxygen atom. This is because sulfur has undergone sp2 hybridization. Still sulfur has one p orbital through which it can form a pi bond. Unless all p orbitals are used up, there is no use of d orbitals. Now the pi 2 bond is formed from pi 2 or pi 3. The remaining 2 pi bonds are formed from the interaction of 3d orbital of sulfur overlapping with 2p orbital of oxygen. Therefore what we can say, there is one p pi bond in SO3, and we have 2 d pi p pi bonds in sulfur trioxide. Please note that in case of sulfur dioxide, what we have only one p pi bond and one d pi p pi bond. In case of sulfur trioxide, what we have one p pi and 2 d pi p pi bonds. So it is very easy to tell. Now I am going to give you a general note. This general note is this. You must take a general note. If central atom is sp3 or using all p orbitals for hybridization, central atom is using all its p orbitals for hybridization and forming pi bond, then that pi bond originates from Nd orbitals. So that originates from Nd orbital of central atom. So if you want, you can easily guess after having some practice, but as a notes I am giving you this important point, that if central atom has undergone sp3 or if it is using all p orbitals, then if it is forming any pi bond, that must come from d orbital, that not from p orbital. Or in other words, you understand that if any p orbital is left unhybridized, primarily that p orbital has been used up to form a pi bonding, and all other extra pi bonds will come from d pi p pi overlap. Therefore in coming molecules, I simplify the notes. I give you very short notes and I give less information. And now let us take example 8, SOCl2. Let us take SOCl2. Now again make a VSEPR prediction of the geometry of the molecule. The geometry of the molecule, yes, double bond O, Cl, and a lone pair. Total we have 4 electronic domains, 1, 2, 3, 4. According to VSEPR, 4 electronic domains should lead to tetrahedral, but among the 4 electronic domains, here one electronic domain is a lone pair. This is a lone pair, and apart from a lone pair, there is another electron domain is a double bond. So the bonded electronic domains are also not identical. Therefore this is pyramidal but not a regular pyramidal. You can call it pyramidal but not a regular pyramidal. Now to find out hybridization, count number of sigma bonds and lone pairs. Now in every double bond there is only one sigma bond, and here one, and here 1, and total 3 sigma bonds. Therefore we have 3 sigma bonds plus, now let us count lone pair. There is 1 lone pair. Altogether it is becoming 4. Then what is a hybridization? We call it is sp3 hybridization. Now I am directly predicting. Here we have sigma bonds. Now we can predict sigma bonds and how the sigma bonds are formed. So there are two sigma bonds. There are two sigma bonds which are formed from sp3 hybrid orbital of sulfur overlapping with 3p orbital of chlorine. There are two such. You can see these two bonds are formed by overlapping of sp3 hybrid orbital of sulfur with that of 3p orbital of chlorine. And we have here one more sigma bond, and there is one more sigma bond, and this sigma bond is formed from overlap of sp3 of S with 2p orbital of oxygen. Chlorine belongs to third period. It has orbitals to overlap in 3p where oxygen belongs to second period. It has 2p orbitals to overlap with hybrid orbitals. Now apart from sigma bonds, it also has a pi bond. Here only one pi bond. You can guess the pi bond comes from. Yes, you can guess the pi bond comes from. See, it is sp3 hybridized, right? As it is sp3 hybridized, there is no unhybridized p orbital to form a pi bond. Therefore, this pi bond must be from d orbital of sulfur. Instead, it is 3d orbital of sulfur forming pi bond with 2p orbital of oxygen atom. Please note that oxygen atom has two unhybridized p orbitals. Oxygen atom has two half-filled p orbitals. One p orbital is used to form a sigma bond and another p orbital is used to form pi bond. Now let us take next example, SO2Cl2. This is the 9th example, SO2Cl2. Immediately make VSEPR drawing, VSEPR structure. S, double bond O, the double bond O, Cl and Cl. So what is the information you get? There are 4 electronic domains, 1, 2, 3, 4, expected structure tetrahedron, but all electronic domains are not identical. These two are one type and these two are another type. Consequently, we cannot call it a regular tetrahedron, and of course it is a distorted. It is a distorted tetrahedron. It is a distorted tetrahedron. Now what is our next idea? We need to calculate total number of sigma and lone pairs. Here there is no lone pair. Number of sigma bonds, you can count 1, 2, in S double bond O 3, in another S double bond O, one more sigma bond 4. So we have 4 sigma bonds and there is no lone pair on the sulfur. Sulfur belongs to 16th group. It has used up all its 6 valency electrons. 4 plus 0 becomes equal to 4. So which hybridization? This is going to be sp3 hybridization. Now we have to write there are sigma bonds and there are pi bonds. Now coming to sigma bonds, how we got a sigma bonds? Here we have a sigma bonds and the sigma bonds are formed from, there are 2 sigma bonds. Each sigma bond is formed from overlap between sp3 hybrid orbital of sulfur with that of 3p atomic orbital of chlorine. 3p atomic orbital of chlorine. And we have 2 more sigma bonds. And we also have 2 more sigma bonds, and the sigma bonds are formed from sp3 hybrid orbital of sulfur overlapping with 2p atomic orbital of oxygen. And apart from that, we have 2 pi bonds. We have 2 pi bonds, and these 2 pi bonds, each pi bond is with 1 oxygen. So these 2 pi bonds are formed by, there are 2 pi bonds formed by, as it is sp3, any pi bond must come from d orbital overlap. So this is 3d orbital of sulfur overlaps with 2p orbital of oxygen, and therefore we got d pi p pi bond. Here we got 2 d pi p pi bonds. Now let us take another example. We are going to take an update, XeO2F2. Let us have a molecule XeO2F2. Now let us make first its Lewis dot prediction, VSEPR prediction, xenon. So Xenon belongs to 18th group. Being 18th group, 8 valency electrons out of 8 with 1 oxygen, 2 electrons, 2 oxygens, 4 electrons and 2 more fluorines and 2 more electrons, total 6 electrons. Therefore, it has a lone pair, and we already have seen its VSEPR structure should be double bond O, double bond O. The fluorine takes axial positions to minimize the repulsions. Please note that the molecular geometry, the location of the lone pairs and the double bonds in that molecular geometry is understood from VSEPR better than valency bond theory. But valency bond theory is just to know the basic geometry and basic way of understanding atomic orbital overlaps, and origin of this overlap leads to the concept of the directionality of a sigma bonds, and as well as how we have different type of bonds like pi bonds. Again, here what is the geometry of the molecule? We call this is actually what we call trigonal bipyramidal, but we call it seesaw because one of the positions occupied by the lone pair. Further, here the problem, the remaining 4 electronic domains are not identical. All are 2 are 1 type and other are 2 type. Here these 2 are 1 type and these 2 are another type. Anyway, we simply call it seesaw structure. Now the important task is to write hybridization. To write hybridization, you have to count total number of sigma bonds. We know that between 2 atoms there is always only 1 sigma bond. As there are 4 atoms, there must be minimum 4 sigma bonds plus 4 sigma bonds and plus there is a 1 lone pair. This is total becoming equal to 5. So to have 5 hybrid orbitals, which hybridization is possible? Yes, it is sp3 dehybridization. Commonly it is sp3d hybridization. Here I am going to make some important point. We got sigma bonds, total how many? 4. Out of 4, 2 sigma bonds are 1 type, and how they are formed? They are formed from sp3d hybrid orbital of sulfur overlapping with 2p orbital of oxygen, and these two are formed from there are 2 such bonds formed from sp3d xenon. It's not sulfur, it's a xenon. sp3 dihybrid orbital of the xenon overlapping with, again fluorine also uses 2p because it is also second period element with fluorine, and of course total 4 sigma bonds done. Now we have pi bonds. We have to count the pi bonds and how they are formed and what overlaps. There are only 1 type of pi bonds, but there are 2 such pi bonds. Now how these 2 pi bonds are formed? These 2 pi bonds are formed from definitely d pi p pi overlap. Why d pi p pi overlap? Because xenon has undergone sp3d hybridization. It has used all of its p atomic orbital. Therefore, they must be formed from xenon belongs to which period? Helium, neon, argon, krypton, xenon. Xenon belongs to 5th period. Therefore, it must use its 5d orbitals to form pi bond with 2p orbital of each 2p orbital of oxygen atom. Therefore, we have 2 pi bonds, that is a molecule XeO2F2. Now let us make another example. That's 11th example. Let us take XeO3. Hereafter I make my calculations a bit faster. Now XeO3, the geometry. What is the geometry? Meanwhile you think. Yes, what is the geometry? It's a pyramidal. This is a pyramidal. Now number of sigma bonds. How many sigma bonds it has? Total 3 sigma bonds, and there is 1 lone pair. So total number is becoming 4. It is therefore xenon sp3 hybridized. Now we have to count pi bonds. We need to count the pi bonds and sigma bonds. We got sigma bonds. Total how many? 3 sigma bonds. All sigma bonds are identical, formed from sp3 hybrid orbital of xenon overlapping with 2p atomic orbital of oxygen, and also we have pi bonds. How many pi bonds? We have 3 pi bonds. Each pi bond must be formed from 5d orbital of xenon overlapping with 2p orbital of oxygen. Why this happened? Because there is no p orbital left for pi bonding. Now let us take another example, XeO4 xenon tetroxide. Just right away, this is very simple molecule. We have Xe double bond O, double bond O, double bond O, the double bond O. What is the geometry we call? According to VSEPR, it's a tetrahedral, and of course it is further, we can claim it is sp3 hybridized. This molecule is sp3 hybridized because there are 4 sigma bonds and there is 0 lone pair, which is equal to 4. It is going to be sp3 hybridized. Now here we can make up sigma bonds. So sigma bonds are formed. How many type of sigma bonds? Here we have only one type of sigma bonds. There are such sigma bonds are 4. Each sigma bond is formed from overlapping of sp3 hybrid orbital of xenon overlapping with 2p atomic orbital of oxygen, and also we have pi bonds, and all these pi bonds are d pi p pi bonds. There are such 4 d pi p pi bonds formed from 5d of xenon overlapping with 2p of oxygen. So we have 4 times d pi p pi bonds. We call them 4 times d pi p pi bond. Till now we have seen some simple molecules. Now let us make another molecule. Here we have seen XeO2F2. Now let us make one more molecule. Then we take some other complex systems. Now let us take XeOF4. Let us take XeOF4. Again, central atom here, xenon, that we are very aware of it. Xenon, it forms a double bond and 1 sigma bond with 1 fluorine. So there are 4 sigma bonds and 1 double bond. Along with that, it has a lone pair. To minimize the repulsion, we have to place the double bond and lone pair at 180, and there are 4 fluorine molecules. Actual structure, we expected octahedral, but actual structure is going to be square pyramid, and strictly speaking it is not perfectly square pyramid, it is a distorted. Only 4 atoms will lie on plane. These 2 fluorine atoms, 3, 4 and 5. Only these fluorine atoms will lie on plane. Xenon will be on out of plane. This is out of plane. Because we are assuming that the double bond and the lone pair are almost having similar extent of repulsions, but this is not always true. There is a slight difference, and therefore the xenon nucleus exactly will not lie on this plane. We may approximate on the plane, so we are writing it as a square pyramid. Now let us count number of sigma bonds and number of lone pairs. We have total 1, 2, 3, 4, 5 sigma bonds, and 1 lone pair, and total becoming equal to 6. If there are total 6, what is the type of hybridization we call? What is the possible hybridization? We take sp3d2 hybridization. We take sp3d2 hybridization. Now here again we have to sketch out. We got sigma bonds, and how many sigma bonds? There are different varieties of sigma bonds. One sigma bond is formed from sp3d2 hybrid orbital of xenon overlapping with 2p atomic orbital of oxygen, and we have 4 more sigma bonds formed from sp3d2 hybrid orbital of xenon, each sp3d2 overlapping with 2p atomic orbital of fluorine, and one sp3d2 contains lone pair. And apart from that, here we have pi bonds also. And how pi bond is formed? This pi bond must be formed from 5d orbital of xenon. Please note that xenon belongs to 5th period, therefore it is going to be 5d of overlapping with 2p orbital of oxygen. 2p orbital of oxygen. This is a simple way of writing hybridizations and then the geometry predictions from VSEPR. Then from the concept of overlapping, we must say that overlap constituting one bond, either sigma or pi bond, must have been formed from set of hybrid orbitals or set of unhybridized orbitals.